Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Take a moment to get comfortable, wherever you are. Let your body settle into the surface beneath you. There's nothing urgent waiting for you here. Where in the world are you watching from? A bedroom window facing the stars? A quiet corner where the day has finally released its hold on you? Wherever you are, you're exactly where you need to be. Tonight, we're going to explore one of the universe's most profound mysteries. What happens inside a black hole? We'll journey from the familiar space around these cosmic giants, through the point of no return, and toward the centre where physics itself transforms into something we're only beginning to understand. It's a journey that spans the lifetime of the universe itself. From the collapse of ancient stars to the distant future when black holes may be the last objects remaining in all of existence. But don't worry, this isn't going to be a frightening descent into darkness. Instead, we'll move slowly and carefully through what we know, what we think we know, and what still waits, mysterious and beautiful beyond our current understanding. By the end, I think you'll find not horror, but wonder. Not fear, but a kind of peace in the face of something so vast it makes our daily concerns seem small and distant. If you enjoy these calm explorations of the cosmos, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with your evenings, for being part of this community of curious minds seeking rest. So settle in, let your shoulders drop away from your ears. Take a slow breath and let it out even more slowly. Let's begin our gentle drift toward the edge of everything. There's nowhere you need to be right now, nothing you need to solve. Just listen and let the story of black holes unfold like the universe itself, vast, patient, and ultimately strangely comforting. What happens inside a black hole? It's a question that has occupied some of the greatest minds in physics for more than a century. It's a question that sounds simple, almost childlike in its directness, but conceals within it some of the deepest mysteries the universe has to offer. When we ask what happens inside a black hole, we're really asking something more profound. What happens when gravity becomes so strong that it breaks the rules of the universe as we understand them? The question matters because black holes aren't some exotic rarity confined to the fevered imaginings of science fiction writers. They're real, they're common, and they're scattered throughout our galaxy and every galaxy we can observe. Right now, at the centre of our Milky Way, there sits a supermassive black hole called Sagittarius A star, containing the mass of more than 4 million suns. It's been there for billions of years, quietly pulling in matter, warping space around itself, existing at the heart of our cosmic home. And the truth is, we don't fully know what happens if you fell into it. We have equations, brilliant mathematical frameworks developed by Einstein and those who came after him. We have observations, stunning images captured by telescope arrays spanning the entire Earth. We have theories, elegant and strange, that push the boundaries of what we thought possible. But we don't have certainty. We can't, because the inside of a black hole is, by its very nature, cut off from us. Light cannot escape from beyond a certain point, and without light, we cannot observe. We are left with mathematics and imagination, trying to describe something that exists beyond the reach of direct experience. This might sound frustrating, this admission of uncertainty at the very beginning of our journey, but there's something beautiful in it too. In an age where we can look up almost any fact in seconds, where we've mapped the human genome and landed rovers on Mars, there remain mysteries that resist us. The inside of a black hole is one of the universe's last truly unknowable places, at least for now. And perhaps in the end, that unknowability is part of what makes them so compelling. What we'll explore tonight isn't a horror story, despite what the darkness might suggest. It's a story about the limits of knowledge and the persistence of wonder. It's about what happens when you push physics to its absolute edge. It's about time and space doing things that seem impossible, about matter compressed to densities that make the centre of a neutron star look empty by comparison. It's about the universe showing us, in the most extreme way possible, that reality is stranger and more wonderful than anything we might have imagined sitting here on our small planet, looking up at the stars. So let's begin with what we can see, with what we know for certain. Let's start outside a black hole, in the space we understand, and then, slowly and carefully, we'll make our way inward. We'll cross boundaries that cannot be uncrossed. We'll watch time do impossible things, and we'll arrive eventually at the very centre, at the singularity itself, where all our understanding breaks down into something new. The journey won't be frightening. It will be contemplative. Because the truth about black holes, the real truth, isn't that they're cosmic monsters waiting to devour us. It's that they're natural consequences of the universe's laws, playing out on scales that dwarf human comprehension. They're beautiful in their inevitability, profound in their simplicity, and they have something to teach us about the nature of existence itself. So take another slow breath. Feel yourself here, solid and present, and know that as we journey toward the centre of a black hole, we're really journeying toward a deeper understanding of the universe we call home, and that brings us naturally to where black holes come from in the first place. To understand what's inside a black hole, we first need to understand how black holes are born, and that story begins with stars, those brilliant spheres of light that have guided humanity since our ancestors first looked up at the night sky. Stars are, in many ways, engines of resistance. For their entire lives, they fight against the force that would crush them out of existence. Inside a star like our Sun, nuclear fusion in the core produces heat and pressure that push outward. This outward pressure exactly balances the inward pull of the star's own gravity. It's a perfect equilibrium, a cosmic balancing act that can last for billions of years. Our Sun has been maintaining this balance for about 4.5 billion years, and it has another 5 billion or so to go. Every second it converts millions of tons of hydrogen into helium, and the energy released from that conversion keeps it inflated, keeps it shining, keeps it fighting against collapse. But all stars eventually run out of fuel. When a star exhausts its nuclear reserves, the outward pressure drops, and gravity, patient gravity that has been waiting all those billions of years, finally wins. What happens next depends on the star's mass. For stars like our Sun, the collapse is relatively gentle. The outer layers drift away into space, forming a planetary nebula, while the core compresses into a white dwarf, an object about the size of Earth, but containing most of the Sun's mass. For more massive stars, though, the story is more dramatic. Stars with more than about 20 times the Sun's mass end their lives in spectacular supernova explosions. These explosions are so bright they can briefly outshine entire galaxies. They're so powerful they forge the heavy elements that make up planets and people, and in their aftermath they leave behind something remarkable, a core so dense that electrons are crushed into protons, forming neutrons. The result is a neutron star, an object perhaps 20 kilometers across but containing more mass than our entire Sun. But even neutron stars aren't the end of the story. If the collapsing core is massive enough, more than about 3 times the Sun's mass, something extraordinary happens. The neutrons themselves cannot withstand the crushing pressure. There is no known force in physics that can stop the collapse. The matter falls inward, compressing without limit, and space-time itself warps so severely that it creates a point of no return, a boundary called the event horizon. This is how a stellar mass black hole is born. In a fraction of a second, the core of a massive star transforms from matter we can understand, even if it's exotic matter like neutron degenerate material, into something else entirely. It becomes a region of space-time so warped that it's essentially cut off from the rest of the universe. Inside the event horizon, all paths lead to the centre. There is no escape, not by any means we understand. The process sounds violent, and it is. But there's also something inevitable about it. something almost peaceful in the way the universe's laws play out to their logical conclusion. A massive star's core has only so many options when it runs out of fuel. For the most massive cores, becoming a black hole isn't a failure or a tragedy. It's simply what happens when you pack enough mass into a small enough space. It's the universe following its own rules. What's remarkable is that we've observed this process, or at least its aftermath, many times. When massive stars explode as supernovae, we can study the light, measure the energy, and sometimes, in the weeks and months that follow, we can detect the X-rays coming from the region where the black hole formed. We can watch as the newborn black hole begins pulling in matter from its surroundings, heating that matter to millions of degrees and causing it to emit radiation we can detect billions of light years away. So black holes aren't theoretical abstractions, they're real objects with real histories. Each one was born from a star that lived and died. And understanding this origin story helps us understand what we're about to explore, because the physics that creates a black hole, the crushing of matter under gravity's inexorable pull, is the same physics that determines what happens inside one. Which brings us to consider what it actually means for something to be a black hole in the first place. The defining feature of a black hole, the thing that makes it what it is the event horizon. This invisible boundary marks the point of no return. Cross it, and you can never come back. Not because you lack fuel for your rockets, and not because the journey would take too long. You can't come back because inside the event horizon, all paths through space-time lead to the centre. The very geometry of space itself has been warped so severely that outward no longer exists as a direction you can travel. Let me try to explain this in a way that makes sense. Imagine you're in a building where all the hallways, all the staircases, all the doors lead only downward. You can choose which hallway to take, which door to open, but no matter what you choose, you're going down. That's somewhat analogous to what happens inside a black hole's event horizon. You can point your spacecraft in any direction you like. You can fire your rockets at full power, but every direction you can possibly travel leads you toward the centre, toward the singularity. The future itself points inward. This size of the event horizon depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers in radius. For Sagittarius A star, the supermassive black hole at the centre of our galaxy, the event horizon is about 12 million kilometers across, roughly the distance from the Sun to Venus. Despite containing 4 million times the Sun's mass, it's spread over a much larger volume, which has interesting consequences we'll explore later. What's crucial to understand is that the event horizon isn't a physical surface. If you could somehow watch someone cross it, from your safe position far away, you wouldn't see them encounter a barrier or a shell. From their perspective, assuming they survived the journey, the crossing would be unremarkable. Space near the event horizon looks much like space slightly farther out. There's no warning sign, no fence, no sudden change. One moment you're outside with the theoretical possibility of escape. The next, you're inside, and escape is no longer possible. The change is absolute, but locally it's subtle. This is one of the strange features of general relativity, Einstein's theory of gravity. In Einstein's framework, gravity isn't a force pulling you down. It's the curvature of space-time itself. Mass warps space, and that warping tells objects how to move. Near a black hole, space is warped so severely that the natural paths objects follow, what physicists call geodesics, curve inward. And inside the event horizon, they curve inward so sharply that nothing, not even light, can follow a path that leads outward. From outside, watching someone approach a black hole, you would see something strange. As they got closer to the event horizon, they would appear to slow down. The light coming from them would be red-shifted, stretched toward longer wavelengths, becoming redder and dimmer. As they reached the event horizon, they would appear to freeze, suspended forever at the boundary. You would never actually see them cross. Time dilation, the way gravity warps time itself, would stretch the final moments before crossing into an infinite duration from your perspective. But for the person falling in, time would pass normally. They would cross the event horizon in a finite time by their own clock. They might not even realise when they crossed, at least not immediately. Only later, if they tried to turn back, would they discover that return was impossible. They would find that their future, all possible futures, lay deeper inside. The event horizon would be behind them, in their past, unreachable as yesterday is unreachable to us. This asymmetry between perspectives, between the outside observer who sees the infalling object frozen forever and the falling object that crosses in finite time, is one of the deep puzzles of black hole physics. Both perspectives are equally valid. Both are describing the same event, yet they seem to contradict each other. It's a hint that our usual ways of thinking about time and space, about before and after, might not fully apply in the extreme environment near a black hole. So the event horizon is a boundary in space-time, a point of no return defined by geometry rather than substance. And it's the first of several strange boundaries we'll encounter on our journey inward. Let's continue now toward that horizon and begin to understand what the journey feels like. Imagine you're in a spacecraft, approaching a black hole. Not a small stellar mass black hole, but something larger, perhaps a black hole with 10,000 times the Sun's mass. You've chosen a larger one deliberately, for reasons we'll understand in a moment. As you draw closer, your instruments start registering the intense gravitational field. Space is visibly warped around you. If there are stars behind the black hole from your perspective, you'd see their light bent around it, creating a bright ring of distorted starlight called an Einstein ring. The black hole itself appears as a perfectly black circle against the star field. Not dark in the way a planet or moon is dark, reflecting no light. Black in an absolute sense. Light that falls toward that circle doesn't bounce back. It simply disappears beyond the event horizon. The absence is total, and if you stared at it long enough, you might start to feel that you're looking not at an object in space, but at a hole in space itself, an absence where something should be, but isn't. As you get closer, you start to notice something strange about time. You've synchronized a clock on your spacecraft with a clock back at a space station orbiting at a safe distance. When you check your spacecraft's clock against signals from the station, you find that the station's clock is running faster than yours. Not by much at first, but measurably faster. The closer you get to the black hole, the more pronounced this effect becomes. This is time dilation, the way that gravity slows time. Astronauts on the International Space Station experience this too, in a tiny way. Their clocks run about 45 microseconds per day faster than identical clocks on Earth's surface, because they're farther from Earth's centre and experiencing slightly less gravity. Near a black hole, the effect is magnified a billionfold. You also start to notice something else, something more immediately concerning. There's a difference in the gravitational pull between your feet, which are closer to the black hole, and your head, which is farther away. This difference, called a tidal force, tries to stretch you. It's the same force that causes Earth's oceans to bulge toward and away from the moon, creating our tides. But near a black hole, the tidal force is extreme. For a small black hole, a stellar mass black hole with just a few times the Sun's mass, these tidal forces would become lethal long before you reach the event horizon. They would stretch you, pulling your body apart in a process that has unfortunately been named spaghettification. But you chose a larger black hole for your journey, remember? And here's the remarkable thing. For a supermassive black hole, one with millions or billions of times the Sun's mass, the tidal forces at the event horizon are actually quite gentle. This seems counterintuitive. How can a more massive black hole have weaker tidal forces? The answer lies in the size of the event horizon. A more massive black hole has a larger event horizon, and the tidal force depends not just on the strength of gravity, but on how quickly gravity changes over distance. At the event horizon of a supermassive black hole, gravity is still incredibly strong, but it's changing relatively gradually. You could, in principle, cross the event horizon of a supermassive black hole without being torn apart. You might not even feel anything unusual at the moment of crossing. This is why physicists often talk about supermassive black holes when discussing what it might be like to cross an event horizon. It's the only scenario where you might survive long enough to experience it. For a stellar mass black hole, you would be destroyed by tidal forces long before you reach the point of no return. For a supermassive black hole, you might cross the event horizon intact, at least for a little while longer. So you continue your approach, monitoring your instruments, watching the clock synchronization drift further and further from the station's time. The black circle grows larger, filling more and more of your view. The distorted starlight around it becomes brighter and more complex, and you realize you're committed now. Even if you fired your engines at full thrust trying to escape, you're close enough that the battle would be lost. The gravitational well is too deep. You've already, in a sense, crossed a boundary. Not the event horizon itself, but another boundary called the innermost stable circular orbit. Inside this orbit, there's no way to circle the black hole indefinitely. All orbits decay. All paths spiral inward. And so we come to the moment itself, the crossing of the horizon. The crossing happens in a moment, and in no moment at all. From your perspective, aboard your spacecraft, time continues to flow normally. Your clock ticks at its usual rate. Your heart beats its familiar rhythm. You check your instruments one final time, and they show elevated gravity readings, extreme space-time curvature, but nothing infinite, nothing that would indicate you're at some special location. You look around, and space appears continuous. There's no barrier, no membrane, no surface to pass through, but then you notice something odd when you look back toward the outside universe. The stars behind you, the station you left, all the matter and light that exists outside the event horizon seems to be accelerating away from you. Time out there, from your perspective, is speeding up. If you could watch long enough, you might see the entire future history of the universe play out in fast forward. Stars would age and die, galaxies would drift apart, the universe would cool and darken. This is the flip side of the time dilation we discussed earlier. From outside, you appear frozen at the event horizon. From inside, looking out, the external universe appears to race toward its distant future. But you can't watch for long. You're falling inward now, and there's no stopping your descent. The tidal forces, gentle at the event horizon of your supermassive black hole, begin to increase. The difference in gravity between your feet and head grows more pronounced. Your body begins to feel the stretch, the pull of the singularity ahead. You've crossed the event horizon, and while that crossing was unremarkable, you're now in a region of space-time that plays by different rules. Here's the strange part, the part that's hard to wrap your mind around. The singularity at the centre of the black hole isn't just ahead of you in space. It's ahead of you in time. Inside the event horizon, the singularity is your future, as inevitable as tomorrow is for us outside. You can no more avoid reaching it than you can avoid reaching the next second. You could fire your engines, you could change direction, you could do anything within the laws of physics, and you would still reach the singularity. It's not that the path to it is inescapable. It's that reaching it is your future, and the future always comes. This is what physicists mean when they say that inside a black hole, space and time swap roles. Outside, you can move freely in space but are dragged inexorably forward in time. Inside, you're dragged inexorably inward toward the singularity in what we think of as space, while your time coordinate, the mathematical quantity that describes your temporal position, becomes something you have freedom to vary. It's deeply strange, deeply counterintuitive, and it shows how thoroughly our everyday notions of space and time break down in extreme conditions. As you fall deeper, the tidal forces continue to grow. Your spacecraft, if it wasn't designed for this, begins to groan under the stress. The difference in gravity from one end of the ship to the other is now extreme enough to deform the structure. If you're still alive, your body is experiencing forces it wasn't designed to withstand. The stretching becomes painful, then catastrophic. This is spaghettification, the process where tidal forces pull objects into long, thin strands. It's an inevitable consequence of the extreme curvature of space this close to the singularity. But even as your body fails, even as your spacecraft tears apart, something remarkable is happening. You're experiencing space-time in a configuration that nothing in the ordinary universe can match. You're in a place where the rules are different, where time and space have traded places, where your future is defined by geometry. You're falling towards something that our best mathematics describes as a point of infinite density and infinite curvature, a singularity where the equations break down and physics as we know it stops making predictions. What happens when you reach that singularity? What is it like at the very centre? That's where we're heading next, to the place where our understanding reaches its limit and speculation begins. But before we get there, before we confront the singularity itself, let's take a moment to understand what we mean when we talk about space-time being curved and what it means for that curvature to become infinite. The journey continues, deeper into mystery. To truly understand what happens inside a black hole, we need to understand gravity not as a force, but as geometry. This is Einstein's great insight, the foundation of his general theory of relativity. Published in 1915 after years of intense mathematical struggle, the theory revolutionized our understanding of gravity and made predictions that still guide our exploration of the universe. In Newton's physics, gravity is a force that reaches across space, pulling objects together. The Earth pulls on the moon pulls on the Earth, and somehow, across the vacuum of space, this force operates. Newton himself found this troubling. He called it, quote, one, and admitted he couldn't explain how it worked. But the mathematics described the motions of planets and moons so accurately that the mystery of the mechanism could be set aside. Einstein proposed something radically different. In his framework, gravity isn't a force at all. Instead, mass and energy warp the fabric of space-time, and objects move along the curves in that fabric. A planet doesn't orbit the sun because it's being pulled by a force. It orbits because the sun's mass has curved space around it, and the planet is simply following the straightest possible path through that curved space, what mathematicians call a geodesic. Think of it like a marble rolling on a stretched rubber sheet. If you place a heavy ball in the centre, it creates a depression, and a marble rolling nearby will curve around it. Not because the heavy ball is pulling on it directly, but because the surface it's rolling on is curved. The analogy isn't perfect because space-time is four-dimensional, and the curvature happens in all dimensions, including time. But it gives you a sense of what Einstein meant. Gravity is geometry. Mass tells space-time how to curve, and space-time tells mass how to move. It's a beautiful, self-consistent framework, and it's been tested countless times. Every time we check, from the bending of starlight during a solar eclipse to the precise timing of signals from GPS satellites, Einstein's equations hold up perfectly. Near a black hole, this curvature becomes extreme. Imagine our rubber sheet again, but instead of a gentle depression from a heavy ball, imagine the sheet being pulled down into an infinitely deep funnel. The sides of the funnel get steeper and steeper as you go down. At some point, these sides become so steep that a marble rolling there could never roll back out. That boundary, where the slope becomes too steep for escape, is analogous to the event horizon, and at the very bottom of the funnel, where the depth becomes infinite, that's analogous to the singularity. The mathematics that describes this curvature is called the metric, and for a non-rotating black hole, it's given by something called the Schwarzschild solution. Named after Carl Schwarzschild, who derived it just months after Einstein published General Relativity. Schwarzschild was serving in the German army during World War I when he worked out the mathematics. He died of an illness contracted on the Eastern Front just a few months after his discovery. He never knew that his solution would become one of the most important in all of physics. describing the space-time geometry around every non-rotating black hole in the universe. The Schwarzschild metric tells us several things. It tells us where the event horizon is, at a radius called the Schwarzschild radius. It tells us how time slows down as you approach that radius. And it tells us that at the very centre, at 0 radius, something strange happens. The curvature becomes infinite. The metric itself breaks down. The mathematical description stops being able to make predictions. This is the singularity, a point where the theory that predicts it also admits its own failure. Physicists generally believe that when a theory predicts a true infinity, it's a sign that the theory is incomplete. Infinities are often signals that we're missing something, that a more complete theory would smooth out the infinity into something finite but perhaps very large. This is one of the great hopes for quantum gravity, the still developing theory that tries to merge general relativity with quantum mechanics. Perhaps quantum effects near the singularity prevent it from being truly infinite. Perhaps space-time itself becomes granular at small scales, and the singularity spreads out into a small but finite region. But we don't know yet, and that brings us to consider what our current theories do tell us about the singularity, and where they admit that our knowledge ends. At the very centre of a black hole, according to general relativity, lies the singularity. This is where all the mass that formed the black hole, plus all the mass that has fallen in since, is concentrated. In the mathematics, it appears as a point of infinite density and infinite space-time curvature. All the matter, all the atoms and particles that once made up stars or planets, or anything else that fell in, is compressed to this single point. The volume is 0. The density is infinite. Time and space cease to behave in ways we can understand. But what does that actually mean? Can something really have infinite density? Can all that mass really be compressed to a point with no size? These questions push at the limits of physics, and the honest answer is that we don't know. The singularity represents the place where our most successful theory of gravity, general relativity, breaks down. It's the point where the equations start producing infinities, and infinities in physics usually mean you've reached the edge of your theory's validity. Think of it this way. Newton's theory of gravity works wonderfully for most purposes. It predicts planetary orbits, describes the motion of projectiles, even lets us navigate spacecraft across the solar system. But at high speeds and strong gravitational fields, Newton's theory breaks down. It makes predictions that don't match reality. Einstein's general relativity fixes these problems, extending our understanding into new regimes. But even Einstein's theory has its limits. At the singularity, where densities and curvatures become infinite, general relativity itself breaks down. It's not that the theory is wrong exactly, it's that it's incomplete. It needs something more. That something more is likely quantum mechanics. Quantum mechanics, the theory that describes the behaviour of particles and fields at very small scales, has its own set of strange features. It introduces uncertainty, makes probability fundamental, describes particles as waves and waves as particles. When physicists try to combine general relativity with quantum mechanics to create a theory of quantum gravity, they run into profound difficulties. The two theories seem to speak different mathematical languages. They make different assumptions about the nature of space and time. Unifying them is one of the great unsolved problems in physics. But most physicists believe that quantum effects must become important at the singularity. At the incredibly small scales and high energies present there, quantum mechanics can't be ignored, and there are hints that quantum effects might smooth out the singularity, might prevent densities from becoming truly infinite. In some proposed theories of quantum gravity, like string theory or loop quantum gravity, space-time itself becomes granular at small scales. There's a minimum meaningful size, a quantum of space, below which the concept of smaller distances doesn't make sense. If that's true, then the singularity might not be a point at all. It might be a tiny region, unimaginably small by everyday standards, but not literally zero-sized. This matters because a true singularity, a point of infinite density, would be a place where physics simply stops. There would be no way to describe what happens there, no way to make predictions, no way to understand the nature of matter and space. But a quantum singularity, smoothed out by quantum effects, might be describable. It would still be extreme, still be beyond anything we've ever encountered, but it would be part of physics, not a breakdown of physics. The other possibility is that there's something even stranger going on. Some theories suggest that the interior of a black hole might connect to other regions of space-time, to other universes, or to distant parts of our own universe. These connections, called wormholes or Einstein-Rosen bridges, emerge from the mathematics of general relativity but come with their own set of problems. They seem to require exotic matter with negative energy to remain stable, and we've never observed such matter. Still, the mathematics allows them, and in the extreme conditions inside a black hole, perhaps they exist. The truth is, we're speculating now. We've left the realm of observation and experiment and entered the realm of theory and imagination. The singularity is hidden behind the event horizon, forever cut off from direct observation. We can't see it, can't measure it, can't send a probe to report back on what it finds. All we have are mathematics, and the hope that the universe's laws continue to apply even in its most extreme corners. And that leads us to consider what else might be hidden inside the event horizon. Not all black holes are the same. So far we've been discussing the simplest kind, a non-rotating black hole described by the Schwarzschild solution. But most black holes in the universe rotate, and rotation changes everything. A rotating black hole is described by a different solution to Einstein's equations, called the Kerr solution, named after Roy Kerr, who discovered it in 1963. The Kerr solution reveals new features, new layers of structure inside a black hole that don't exist in the non-rotating case. When a massive star collapses to form a black hole, it carries its angular momentum with it. Stars rotate. Our sun rotates, taking about 25 days to complete one turn. More massive stars often rotate faster. When such a star's core collapses, conservation of angular momentum means the resulting black hole spins rapidly, like a figure skater pulling in her arms. The event horizon of a rotating black hole isn't spherical but flattened, bulging at the equator, oblate like a squashed sphere. More remarkably, a rotating black hole drags spacetime around with it. This effect, called frame dragging, happens to some extent around any rotating mass. Earth drags spacetime very slightly, an effect so small it took exquisitely precise experiments to measure. But around a rotating black hole, frame dragging is extreme. Space itself is pulled around in the direction of the black hole's rotation. If you tried to remain stationary near a rotating black hole, you would find yourself being pulled along, swept up in the current of rotating space-time. It's as if space itself has become a whirlpool and you're caught in the flow. This rotating space-time creates a region called the ergosphere, outside the event horizon but still profoundly affected by the black hole's spin. Inside the ergosphere you can't remain stationary with respect to distant stars. You must rotate along with the black hole, at least partially. You could still escape from the ergosphere, unlike from inside the event horizon, but escape would require you to move against the flow of space itself. It's like swimming in a river. You can swim across it. You can even swim upstream if you're strong enough, but you can't remain perfectly still with respect to the riverbank. The current carries you along whether you like it or not. The interior of a rotating black hole is even stranger than that of a non-rotating one. Instead of a single event horizon, a rotating black hole has two, an outer event horizon and an inner event horizon. Between them, the structure of space-time is different from what we've discussed so far, and inside the inner horizon, the mathematics suggests something truly bizarre, a ring-shaped singularity rather than a point singularity. In the Schwarzschild case, the singularity is a point at the centre, but in the Kerr case, the singularity is a ring, spinning at the equator of the black hole. This ring singularity has strange properties. The mathematics suggests that if you could somehow pass through the ring without being destroyed, you might emerge into a region of space-time that's no longer inside the black hole. In some interpretations, you might emerge into a different universe entirely, or into a region of negative space where gravity repels rather than attracts. These solutions are so strange that most physicists suspect they're not physically real, that something, perhaps quantum effects or instabilities we haven't fully understood, would prevent these exotic behaviours from actually occurring. But we can't be sure. The interior of a rotating black hole, especially the region near the ring singularity, is so far removed from anything we can observe or experiment with that our intuitions might be completely wrong. The mathematics of general relativity allows these strange solutions, and general relativity has been right about so many things that we can't simply dismiss what it tells us about black hole interiors. What we can say is that rotation adds complexity and structure to black holes. It adds layers, regions with different properties, possibilities that don't exist in the non-rotating case. And since most black holes in the universe likely do rotate, since angular momentum is ubiquitous in cosmic processes, these strange structures might be the norm rather than the exception. Every black hole might contain within itself an inner horizon, an ergosphere, a ring singularity, all hidden forever from external view. And this brings us to consider what physical processes occur as matter falls into these structures. Matter doesn't just disappear when it crosses an event horizon. It continues to exist, continues to interact, continues to follow physical laws, at least for some time. What happens to that matter as it falls toward the singularity? How does it behave in the extreme environment inside a black hole? These questions touch on some of the deepest puzzles in theoretical physics, connecting gravity to quantum mechanics in ways we're only beginning to understand. When matter crosses the event horizon, it's often moving at enormous speed. Anything falling into a black hole accelerates as it falls, just as a stone accelerates when you drop it toward Earth. By the time matter crosses the event horizon of a stellar mass black hole, it might be moving at a significant fraction of the speed of light. This matter brings with it energy, momentum, and quantum information about its previous state. Where does all this go? According to classical general relativity, it all ends up at the singularity. The infalling matter follows its geodesic path through curved space-time, and that path terminates at the singularity in a finite proper time, the time measured by a clock travelling with the matter. For a stellar mass black hole, this time might be a fraction of a second. For a supermassive black hole, it might be hours, but eventually, inexorably, the matter reaches the centre. But here's where things get interesting. Matter isn't classical. Matter is quantum mechanical. At the microscopic level, particles don't have definite positions until measured. They exist in superpositions of states. They can become entangled with other particles, sharing quantum information across space. What happens to these quantum properties as matter falls into a black hole? This is the realm of the black hole information paradox, one of the most debated questions in theoretical physics. The paradox arises because quantum mechanics insists that information can't be destroyed. If you know the complete quantum state of a system at one time, the laws of quantum mechanics let you calculate the state at any other time, past or future. Information is conserved. But if matter falls into a black hole and ends up at the singularity, and the singularity is cut off from the external universe by the event horizon, how can that information ever be retrieved? It seems to be lost forever, violated the principle of information conservation. Stephen Hawking realised this was a problem in the 1970s. His work on black hole radiation, which we'll discuss more later, suggested that black holes can eventually evaporate, shrinking and disappearing as they emit thermal radiation. But if the radiation is thermal, meaning it has no special structure or encoded information, and if the black hole eventually disappears completely, then the information about everything that fell in would be permanently lost. The universe would forget what those particles used to be. Quantum mechanics would be violated. Physicists have proposed many solutions to this paradox. Some suggest that information is somehow encoded in the Hawking radiation after all, emerging in subtle correlations that we don't yet understand how to calculate. Others propose that information is stored at the event horizon itself, in what's called a holographic description of the black hole's interior. Still others suggest that information might escape through wormholes or other exotic structures. The debate continues, and it involves some of the best minds in physics, because resolving it will likely require a deep understanding of quantum gravity. What we can say is that matter falling into a black hole doesn't just disappear in a classical sense. Its quantum properties, its information, somehow persist, encoded somewhere in the structure of space-time. Maybe that encoding is at the event horizon. Maybe it's in the radiation the black hole emits. Maybe it's in structures we haven't even thought of yet. But the universe seems reluctant to let information truly vanish. For the matter itself, the physical atoms and particles, the journey is one of increasing compression and energy. As the tidal forces grow, molecules are torn apart into atoms. Atoms are torn apart into nuclei and electrons, and eventually even nuclei are crushed. The matter becomes plasma, then something beyond plasma, something so hot and dense that our understanding of states of matter breaks down. By the time it reaches the singularity, if it reaches the singularity, it has been transformed beyond recognition. But the matter isn't the whole story. Black holes also affect the very fabric of space-time around them, creating effects that we can observe from outside. And those effects give us clues, indirect but powerful, about what might be happening inside. Let's turn our attention now to what black holes do to the universe around them. The tidal forces inside a black hole aren't just a danger to infalling matter. They're a fundamental feature of how gravity works in extreme conditions, and they tell us something profound about the nature of space-time itself. When we talk about tidal forces in everyday life, we're talking about the difference in gravitational pull across an extended object. The moon pulls more strongly on the side of Earth closest to it than on the side farthest away, and this difference creates our ocean tides. Near a black hole, these tidal forces are amplified enormously. The difference in gravitational pull between your head and your feet, if you're falling feet first toward a stellar mass black hole, becomes so great that it would pull you apart long before you reach the event horizon. This spaghettification effect is real and unavoidable for stellar mass black holes. Your body would be stretched into a thin stream of atoms, then a stream of particles, then a stream of elementary particles, all falling in a line toward the centre. But remember, for a supermassive black hole, the tidal forces at the event horizon are much gentler. You could cross the event horizon intact. The tidal forces would still be there, still be increasing as you fell deeper, but they would only become lethal closer to the singularity. This means there's a region inside a supermassive black hole where you could, in principle, survive for a while. You would be doomed, falling inevitably toward the centre, but you might have time to think, to observe, to experience the strange environment you find yourself in. What would that experience be like? The tidal forces would make themselves felt as a gentle stretch at first, growing stronger over time. You would feel as if you were being pulled lengthwise and compressed widthwise, as if invisible hands were moulding you like clay. The sensation would be uncomfortable, then painful, then catastrophic. But in those moments before it became unbearable, you might notice other effects. Time dilation would be extreme. If you could still see the universe outside, which becomes increasingly difficult as the light falling in with you is red-shifted and distorted, you would see it aging rapidly. The stars outside would be running through their life cycles in fast forward from your perspective. The universe would be rushing toward its future while you fell toward your end. The curvature of space would be visible if you had the right instruments. Light paths would curve dramatically. If you shone a flashlight, the beam might curve back toward you. Straight lines would appear curved. The geometry of space would be so warped that Euclidean geometry, the geometry you learned in school where parallel lines never meet, and the angles of a triangle summed to 180 degrees, would no longer apply. You would be living in a space of non-Euclidean geometry, where the rules are different. You might also notice quantum effects, if your instruments were sensitive enough and if you survived long enough. Near the singularity, quantum effects should become important. The Heisenberg uncertainty principle says that you can't simultaneously know both the position and momentum of a particle with perfect precision. Near the singularity, where space-time curvature is extreme, this uncertainty might manifest in unusual ways. Space-time itself might start to behave quantum mechanically, fluctuating and uncertain. These quantum fluctuations are one reason physicists believe we need a theory of quantum gravity to fully describe the singularity. General relativity treats space-time as smooth and continuous at all scales. But quantum mechanics suggest that at small enough scales, everything, even space-time itself, should be quantized, broken into discrete units. The singularity might be the place where these quantum properties of space-time become unavoidable, where the smooth fabric of Einstein's space-time gives way to something more granular and discrete. All of this remains theoretical, of course. No one has ever experienced the interior of a black hole and returned to describe it. No probe will ever send back data from inside the event horizon. All we have are the mathematics of general relativity, the principles of quantum mechanics, and our imagination. But these tools have served us well in other extreme environments. They've predicted the existence of neutron stars and black holes themselves. They've described the Big Bang and the expansion of the universe. Perhaps they're also giving us genuine insight into what happens in the most extreme environment nature allows. And yet, there's another way to learn about black hole interiors, an indirect way that doesn't require anyone to fall in. We can study what black holes do over long time scales. We can examine how they interact with the quantum vacuum. And this brings us to one of Hawking's most remarkable discoveries. In 1974, Stephen Hawking made a discovery that shocked the physics community and remains one of the most important insights into black hole behaviour. He showed that black holes aren't perfectly black. They emit radiation. They glow very faintly with thermal radiation that we now call Hawking radiation. This discovery emerged from a careful consideration of quantum mechanics near the event horizon, and it suggests that black holes have a temperature and gradually evaporate over time. The mechanism behind Hawking radiation involves the quantum vacuum, the state of empty space in quantum field theory. In quantum mechanics, a vacuum isn't truly empty. It's filled with quantum fluctuations, pairs of particles and antiparticles that spontaneously appear and then annihilate each other almost instantly. These virtual particles exist only for a moment, borrowing energy from the vacuum in accordance with Heisenberg's uncertainty principle, then giving it back when they recombine. Normally, these fluctuations don't have any observable effect. The particles appear and disappear so quickly and over such small distances that they don't influence anything we can measure directly. But near a black hole's event horizon, something remarkable happens. If a particle-antiparticle pair appears just outside the event horizon, one particle might fall into the black hole while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. The infalling particle has negative energy from the perspective of an outside observer, and this negative energy reduces the black hole's mass. This is Hawking radiation. The black hole emits particles, and in doing so it slowly loses mass. The process is incredibly slow for large black holes. A stellar mass black hole, one with several times the Sun's mass, has a temperature far lower than the cosmic microwave background radiation that fills the universe. It would actually gain mass by absorbing radiation from the surrounding space faster than it loses mass through Hawking radiation. Such a black hole would take far longer than the current age of the universe to evaporate noticeably. But smaller black holes, if they exist, would be hotter. The temperature of a black hole is inversely proportional to its mass. A black hole with the mass of a mountain might have a temperature of a few degrees above absolute zero. A black hole with the mass of an asteroid might glow in the infrared, and a tiny black hole, one with the mass of a ship or a building, would be intensely hot, radiating energy at a tremendous rate and evaporating in seconds or minutes. We've never observed Hawking radiation directly. We can't, because even if small black holes exist, they would be incredibly rare and difficult to detect. But the theoretical framework that predicts Hawking radiation is the same framework that successfully describes many other quantum phenomena. Physicists are confident that Hawking radiation is real, even if we haven't yet confirmed it experimentally. What Hawking radiation tells us about the interior of a black hole is profound. It suggests that black holes aren't eternal. They have lifetimes. Given enough time, a black hole will evaporate completely, shrinking as it radiates away its mass. For a stellar mass black hole, this lifetime is immense, far longer than the current age of the universe. The black hole at the centre of our galaxy would take something like 10 to the power of 97 years to evaporate, a number so large it defies comprehension. But eventually it would. This evaporation raises deep questions. If a black hole eventually disappears completely, taking with it the singularity and everything that fell in, what happens to the information encoded in all that matter? This is the information paradox we mentioned earlier. Hawking himself initially thought that information was destroyed, that black hole evaporation represented a fundamental violation of quantum mechanics. But later in his life, he changed his mind, coming to believe that information must be preserved somehow, perhaps encoded in subtle correlations in the Hawking radiation. The debate over black hole information continues to drive research in theoretical physics. It's connected to efforts to understand quantum gravity, to develop a theory that successfully merges general relativity with quantum mechanics. The resolution might tell us something fundamental about the nature of reality itself, about how information and space-time and quantum mechanics fit together. For now, what we can say is that black holes are not the permanent features of the universe they might appear to be. They're dynamic objects with lifetimes and temperatures. They interact with the quantum vacuum in ways that cause them to radiate and shrink. And this slow evaporation suggests that even the most extreme objects in the universe aren't beyond the reach of quantum mechanics, which leads us to ask what other quantum effects might be important inside a black hole. When we try to understand what happens at the very centre of a black hole, we're forced to confront the limits of general relativity and the necessity of quantum mechanics. General relativity is a classical theory, meaning it doesn't include the uncertainty and probability that quantum mechanics insists are fundamental to nature. Near the singularity, where densities and curvatures become extreme, quantum effects can no longer be ignored. But we don't yet have a complete theory of quantum gravity that tells us exactly what those effects are. What we do have are hints and partial theories. String theory, for example, proposes that the fundamental constituents of reality aren't point particles but tiny vibrating strings. These strings exist in a space with more dimensions than the 3 of space and 1 of time that we experience. In string theory, the singularity might be avoided because strings have a finite size. They can't be compressed to a point. This means the singularity might be smeared out into a small but finite region, and the infinite densities predicted by general relativity might be artifacts of treating matter as point particles. Loop quantum gravity takes a different approach. It suggests that space-time itself is quantized, that there's a smallest meaningful unit of space and time. If you try to probe distances smaller than the Planck length, which is about 10 to the minus 35 meters, the concept of distance itself breaks down. In this framework, the singularity can't exist as a point of infinite density, because there's no such thing as a point in quantum space-time. Space is fundamentally discrete, made of tiny building blocks, and the singularity is replaced by a region of extremely high but finite curvature. Both of these approaches are speculative, and neither is complete or fully tested. But they share a common theme. Quantum effects become important at small scales and high energies, and these effects might prevent the true infinities that general relativity predicts. The singularity might not be singular at all. It might be a quantum region where space-time behaves in ways we're only beginning to imagine. This matters because if the singularity isn't truly infinite, if it's a quantum object with finite properties, then it might be described by physical laws. We might be able to make predictions about it. And if we ever develop a full theory of quantum gravity, we might be able to understand not just that black holes have interiors, but what happens there at the deepest level. One possibility that emerges from some approaches to quantum gravity is that the interior of a black hole might connect to other regions of space-time. Wormholes, theoretical tunnels through space-time, are solutions to Einstein's equations. They've been studied extensively, and while they seem to require exotic matter with negative energy to remain stable, they're not forbidden by the mathematics of general relativity. Some physicists have speculated that the interior of a black hole might contain a wormhole connecting to another part of the universe, or to another universe entirely. If such connections exist, they would be one way. You could fall through a black hole and emerge somewhere else, but you couldn't use the same path to return. The event horizon is still a point of no return, but the interior might be richer and more complex than the simple picture of geodesics terminating at a singularity. It might be a hub, a junction point where multiple regions of space-time meet. These ideas remain highly speculative. We have no evidence that wormholes exist, and the requirements for their stability seem difficult to meet. But the mathematics allows them, and in the quest to understand quantum gravity, physicists must follow where the mathematics leads. If the universe permits wormholes, and if they're connected to black hole interiors, then the question _quote_3 underscore has an answer, stranger than we might have imagined. Perhaps it's a doorway to somewhere else. Even without wormholes, the quantum interior of a black hole should be fascinating. Quantum field theory in curved space-time, the framework used to derive Hawking radiation, makes predictions about what kinds of particles and fields can exist near the singularity. There might be intense particle creation, with pairs of particles and antiparticles being produced by the extreme gravitational field. There might be quantum entanglement on cosmic scales, with particles inside the black hole remaining entangled with particles outside. The physics might be so rich and strange that we can't fully describe it without tools we haven't yet invented. But there's another way to think about black hole interiors, one that doesn't focus on the singularity or the quantum mechanics, but on the global structure of space-time itself. And that brings us to consider what black holes mean for the shape and fate of the universe. One of the most intriguing solutions to Einstein's equations is the Einstein-Rosen bridge, better known as a wormhole. These theoretical structures connect two separate regions of space-time through a shortcut, a tunnel that allows travel between distant locations without traversing the space in between. In the 1930s, Einstein and his colleague Nathan Rosen showed that black holes, as described by the Schwarzschild solution, mathematically contained such bridges. The original Einstein-Rosen bridge connects two event horizons in different regions of space-time. You might imagine it as a tunnel, where one end is a black hole and the other end is a white hole, a hypothetical object that's the time reverse of a black hole. Matter can't fall into a white hole, it can only emerge from one. White holes seem to violate the second law of thermodynamics and have never been observed, but they're allowed by the mathematics of general relativity, which treats time symmetrically. The problem with the Einstein-Rosen bridge is that it's not traversable. If you try to use it to travel from one universe to another, or from one part of our universe to another, you would find that the throat of the wormhole collapses too quickly. You would need to travel faster than light to make it through before the tunnel pinches off, and faster than light travel is forbidden by relativity. So while the mathematics allows the bridge to exist, it doesn't allow anything to actually use it. Later work by physicists including Kip Thorne showed that you could, in principle, hold a wormhole open if you had access to exotic matter with negative energy density. Such matter would have negative gravity, pushing space apart rather than pulling it together. The negative energy would prevent the wormhole's throat from collapsing, keeping it open for travellers to pass through. But exotic matter of this kind has never been observed. We've never found anything with negative energy density that could do the job. Still, the fact that wormholes are solutions to Einstein's equations, even if they require exotic matter to be traversable, has led physicists to wonder whether they might exist naturally in some form. Perhaps the interiors of black holes contain wormhole-like structures. Perhaps rotating black holes, with their ring singularities, have more complex topologies that include shortcuts through space-time. Perhaps in the full theory of quantum gravity. When we understand how space-time behaves at the Planck scale, we'll find that wormholes emerge naturally from the quantum foam. These are speculations, and it's important to be clear about that. We have no evidence that traversable wormholes exist. We have no evidence that the interior of any real black hole contains a bridge to anywhere else. But the mathematics is suggestive, and it reminds us that our understanding of space-time might be incomplete. General relativity allows for space-time geometries far stranger than the relatively simple spaces we experience in everyday life. What's fascinating is that these speculative structures connect to deep questions in quantum mechanics. In recent years, physicists have discovered connections between wormholes and quantum entanglement, the phenomenon where two particles can share a quantum state even when separated by large distances. Some theories suggest that entanglement and wormholes might be two different descriptions of the same underlying phenomenon. If two particles are maximally entangled, perhaps they're connected by a tiny wormhole in space-time. If that's true, then the quantum entanglement happening constantly in the universe around us might be weaving space-time together, creating connections at scales we can't directly observe. This idea, sometimes summarized by the phrase quote 4, linking Einstein-Rosen bridges with Einstein-Podolsky-Rosen entanglement, is one of the most exciting developments in theoretical physics in recent decades. It suggests that quantum mechanics and general relativity, those two great theories that seem so different, might be deeply connected in ways we're only beginning to understand, and black holes, with their extreme conditions and their hidden interiors, might be the key to unlocking that connection. Of course, even if wormholes exist inside black holes, you couldn't use them for travel, at least not survival. The tidal forces would destroy you long before you reached any wormhole throat. The radiation and extreme curvature would be lethal. Even if there was somewhere to go, you wouldn't survive the journey. So these structures, if they exist, are more about the fundamental nature of space-time than about practical applications. But they remind us that black hole interiors might be richer and stranger than we imagine. They might not be simple funnels ending in singularities. They might be complex structures, quantum and classical properties intertwined, connecting to aspects of physics we haven't fully explored. And that possibility brings us to consider how black holes fit into the larger story of the universe. Black holes aren't isolated phenomena. They're part of the cosmic ecosystem, playing roles in the evolution of galaxies, the formation of structure in the universe, and possibly even in the universe's ultimate fate. Understanding what's inside a black hole connects to understanding how the universe works on the larger scales. Let's step back now and consider black holes in their cosmic context, how they form, how they grow, and what they mean for the future of everything. We've already discussed how stellar mass black holes form from the collapse of massive stars. But supermassive black holes, the giants at the centres of galaxies containing millions or billions of solar masses, have a different origin story. We don't fully understand how they form. Some might have grown from stellar mass black holes through accretion, pulling in matter from their surroundings over billions of years. Others might have formed more directly from the collapse of massive gas clouds in the early universe. The question of how supermassive black holes grew so large so quickly is one of the open puzzles in astrophysics. What we do know is that these supermassive black holes have profound effects on their host galaxies. As matter falls toward a supermassive black hole, it forms an accretion disk, a swirling disk of gas and dust orbiting the black hole and gradually spiralling inward. Friction in this disk heats the matter to millions of degrees, causing it to emit intense radiation. This radiation, ironically coming from the region just outside the black hole's event horizon, can be so bright that it outshines the entire galaxy. These objects are called quasars, or active galactic nuclei, and they're among the brightest objects in the universe. The energy from these active galactic nuclei can drive powerful winds and jets that blow matter out of the galaxy at high speeds. These outflows can shut down star formation, regulating the galaxy's growth. In this way, supermassive black holes, despite being tiny compared to their host galaxies, can control the evolution of those galaxies. There's even a correlation between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, suggesting a deep connection between black hole growth and galaxy evolution. Black holes also play a role in the large-scale structure of the universe. When black holes merge, an event we can now detect through gravitational waves, they emit ripples in spacetime that carry energy away from the system. These gravitational wave detections have opened a new window on the universe, allowing us to observe black hole mergers that happened billions of years ago in distant galaxies. Each detection teaches us something about the population of black holes in the universe, their masses, their spins, their distribution. Looking far into the future, black holes might be the last surviving objects in the universe. As the universe expands and cools, stars will eventually exhaust their fuel and die. Galaxies will drift apart, separated by ever-increasing distances. The cosmic microwave background will redshift into undetectability. Matter itself might slowly decay, if protons are unstable, as some theories suggest. In this far future, black holes would remain, slowly evaporating through Hawking radiation. The timescales are almost incomprehensible. A solar mass black hole would take 10 to the 67th years to evaporate. A supermassive black hole could last 10 to the 100th years or longer. During this time, the universe would be cold and dark, with black holes as the only remaining sources of energy, radiating away their mass particle by particle. Eventually, even the black holes would evaporate completely, leaving behind a universe of scattered particles and radiation, approaching ever closer to a state of maximum entropy. This distant future is speculative, dependent on assumptions about the stability of protons and the ultimate fate of the universe's expansion. But it's a reminder that black holes aren't just objects in space. They're participants in the universe's story. From the early formation of galaxies to the potential heat death trillions upon trillions of years from now, what happens inside them matters not just for theoretical physics, but for our understanding of cosmic evolution. And there's a poetic quality to this, isn't there? Black holes, the darkest objects in the universe, might be the last lights to go out. Through Hawking radiation, they'll glow faintly for unimaginable ages, the final embers of a universe that has otherwise gone cold. Inside them, hidden behind event horizons, is matter from stars that died billions of years ago, matter that won't reach the singularity for ages yet, matter that carries within it the history of the cosmos. Let's continue now to consider what all of this means for us, for how we understand our place in a universe that contains such extraordinary objects. It might seem strange to talk about human connection when discussing objects as remote and extreme as black holes. What do these cosmic giants with their warped space-time and hidden singularities have to do with us? We'll never visit one. We'll never probe their interiors directly. They exist in a realm so far removed from everyday experience that they might as well be in another universe. And yet, there's something deeply human about our fascination with them, about our need to understand what happens inside even though we can never see it for ourselves. Part of this fascination is simple curiosity, the same drive that makes us look under rocks to see what lives there or peer through telescopes to see what lies beyond our atmosphere. Humans are curious creatures. We want to know things, even impractical things. Even things that have no direct bearing on our survival. Black holes are the ultimate expression of this curiosity. They're mysteries that resist easy answers, phenomena that push the limits of our understanding. Asking what's inside a black hole is, in a sense, asking what the universe is made of at its most fundamental level. But there's more to it than curiosity. Black holes touch on profound questions about existence. They force us to confront the limits of knowledge. Inside the event horizon is a region we can never observe, never probe, never know directly. All our science, all our technology, all our cleverness can't breach that barrier. Light itself can't escape to bring us information. We are left with mathematics and theory, with our ability to reason about things we can't see. This is both humbling and empowering. It's humbling because it shows us that there are limits to what we can know. But it's empowering because it shows that human reason can reach beyond direct experience, can describe realities we'll never personally encounter. Black holes also confront us with the nature of time and the inevitability of endings. Inside a black hole, the future is the singularity. There's no escape from it, no way to avoid it. This is a powerful metaphor for mortality, for the way that time moves in only one direction, and the future is something we can't prevent, only meet. We're not falling into black holes, but we are moving through time toward futures we can't escape. Perhaps this parallel is part of why black holes capture our imagination. They're cosmic expressions of themes we grapple with in our own lives. There's also beauty in the mathematics of black holes, a beauty that scientists spend careers exploring. Einstein's equations, which describe how matter and energy warp spacetime, are elegant in their compact form. The solutions to those equations, the Schwarzschild solution and Kerr solution that describe black holes, have a mathematical beauty that appeals to physicists and mathematicians. It's a beauty based on symmetry and simplicity, on the way complex phenomena emerge from relatively simple rules. Understanding this beauty doesn't require you to follow every mathematical detail. It's enough to know that the universe's laws are consistent, that they apply even in the most extreme circumstances, that a star's collapse and a black hole's formation follow logically from principles we can write down and reason about. And perhaps most importantly, black holes remind us of our place in the cosmos. They show us that the universe is stranger and more wonderful than anything we could have imagined if we'd never looked beyond our own planet. They show us that reality operates on scales far beyond human experience, from the vast event horizons of supermassive black holes to the quantum fluctuations near singularities. We live on a small planet orbiting an ordinary star in an unremarkable galaxy, but we have the capacity to understand objects that exist at the extremes of physical law. That capacity, that ability to reason about the infinite and the infinitesimal, might be humanity's most remarkable feature. So when we ask what happens inside a black hole, we're really asking deeper questions. We're asking what the universe is like in places we can never go. We're asking whether our theories and mathematics can describe realities beyond our experience. We're asking about the nature of knowledge and the limits of understanding. These are philosophical questions as much as scientific ones, and they connect to how we think about ourselves and our place in existence. Let's continue our journey now, deeper into the implications of what we've learned. There are still mysteries to explore, still aspects of black hole interiors that touch on the most fundamental questions in physics. The journey isn't over. In many ways, it's just beginning. In 2012, a group of physicists proposed something startling about black hole event horizons. They suggested that the event horizon might not be the smooth, unremarkable boundary we've been describing. Instead, it might be a firewall, a region of intense energy where anything crossing it would be instantly incinerated. This proposal, which came to be called the AMPS Firewall Paradox after its proponents Almheri, Marolf, Polchinski and Sully, has sparked intense debate and reveals deep tensions between quantum mechanics and general relativity that we haven't yet resolved. The firewall paradox arises from considerations about quantum entanglement and information conservation. When Hawking radiation is emitted from a black hole, the particles that escape become entangled with each other in a specific way that preserves information. But those same particles should also be entangled with particles inside the black hole. They're partners from the virtual particle pairs that created the Hawking radiation in the first place. The problem is that a particle can't be maximally entangled with two different systems at once. This is a fundamental restriction in quantum mechanics called the monogamy of entanglement. Something has to give. Either the entanglement between the Hawking radiation particles isn't maximal, which means information isn't fully preserved in the radiation, violating quantum mechanics, or the entanglement between outgoing particles and their partners inside the black hole is broken, which would release enormous energy at the event horizon, creating a firewall. Both options seem unacceptable, but the mathematics seems to force us to choose one or the other. If firewalls exist, then the picture we've been painting of gently crossing the event horizon of a supermassive black hole would be wrong. You wouldn't survive the crossing. You wouldn't have time to notice anything unusual about the interior. You would be destroyed instantly by a wall of high-energy particles at the boundary. The event horizon would be deadly in a way we haven't previously discussed, not because of tidal forces which can be gentle for large black holes, but because of quantum effects that make the boundary itself lethal. Many physicists find the firewall proposal unsettling. It violates the equivalence principle, a cornerstone of general relativity that says local physics in free fall should be the same everywhere. If there's a firewall at the event horizon, then the event horizon is a special place, detectable by local measurements. You would know when you crossed it because you would be destroyed. This seems to contradict the smooth, unremarkable crossing that general relativity predicts. Various resolutions to the paradox have been proposed. Some physicists suggest that information is released from black holes much earlier than we thought, before the black hole is evaporated enough to create the entanglement problem. Others propose that space-time itself might have a more complex structure than we realize, with connections between the interior and exterior of the black hole that allow information to escape without violating entanglement monogamy. Still others suggest that our understanding of quantum mechanics in curved space-time is incomplete, and that new physics we haven't discovered yet will resolve the paradox. The debate continues, and it's a reminder that our understanding of black holes is still evolving. Despite a century of work since Einstein first formulated general relativity, despite decades of work on quantum field theory and curved space-time, we still don't fully understand how these theories fit together. Black holes, and specifically their interiors and boundaries, are the testing ground where these theories clash. The Firewall Paradox is one example of that clash, a place where our theories seem to give contradictory answers and we don't yet know which to trust. What's remarkable is that this is a theoretical debate about the nature of horizons and entanglement, with no immediate prospect of experimental resolution. We can't visit a black hole's event horizon to check whether there's a firewall. We can't measure the entanglement structure of Hawking radiation directly, assuming we could even detect Hawking radiation at all. We're forced to rely on consistency arguments, on our intuition about how physics should work, on the elegance and simplicity of competing theories. It's physics at its most abstract and mathematical, far removed from experiment, but driven by a desire to understand reality as deeply as possible. The firewall debate shows that even basic questions about black holes, questions like what happens when you cross the event horizon, remain open. We thought we knew the answer. General relativity gives a clear prediction, but quantum mechanics seems to complicate that picture in ways we're still working to understand. And this brings us to consider another way that quantum mechanics affects our understanding of black hole interiors. One of the most profound ideas to emerge from black hole physics is the holographic principle. This principle suggests that all the information contained in a volume of space can be described by information encoded on the boundary of that space. In the case of a black hole, all the information about the interior, about everything that has fallen in and everything happening inside, might be encoded on the event horizon itself. It's as if the three-dimensional interior is a hologram projected from the two-dimensional surface. The holographic principle arose from studies of black hole entropy. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizons, not the volume of their interiors. This was surprising. Usually entropy, which measures disorder or the number of possible microscopic states, scales with volume. The more space you have, the more ways you can arrange things. But for black holes, the entropy depends on area. This suggests that the fundamental degrees of freedom, the things that can vary and create different states, live on the surface, not in the interior. Think of it this way. Imagine encoding information on a hard drive. Normally, you'd expect that a bigger hard drive with more volume can store more information. But black holes don't work that way. The amount of information a black hole can contain is determined by its surface area. If you tried to cram more information into a black hole by throwing matter into it, the event horizon would grow, increasing the surface area and allowing the additional information to be encoded there. But the information density would remain tied to the area, not the volume. This has led physicists to wonder whether our usual picture of space as three-dimensional might be incomplete. Perhaps the three dimensions we experience are somehow emergent from information encoded on lower dimensional surfaces. Perhaps space itself is a hologram, and the fundamental description of reality lives on the boundaries of regions rather than in their interiors. This is speculative, and working out the details is an active area of research, but the mathematics of black holes strongly suggests it. In string theory, the holographic principle takes concrete form in something called the ADS/CFT correspondence. This is a mathematical equivalence between a gravitational theory in a space with a particular geometry, called anti-de Sitter space, and a quantum field theory without gravity living on the boundary of that space. The correspondence is exact, meaning every question you can ask in one theory has a corresponding question in the other, and the answers match. It's as if the gravitational theory in the interior is a holographic projection from the field theory on the boundary. While the ADS/CFT correspondence applies to a specific kind of space-time that isn't exactly like our universe, it provides a concrete example of how holography can work. It shows that gravity, space-time, and even extra dimensions can emerge from a theory that doesn't explicitly include them. In the boundary theory, there's no notion of space beyond a certain number of dimensions. Yet the gravitational theory it corresponds to has an additional dimension of space and describes black holes, horizons, singularities, all the features we've been discussing. What does this mean for the interior of a black hole? If the holographic principle is correct, then everything happening inside a black hole is encoded on its event horizon. The falling matter, the approach to the singularity, the quantum fluctuations, all of it can, in principle, be described by information on the surface. This doesn't mean the interior doesn't exist. It means the interior and the boundary description are two ways of looking at the same physics, like how a hologram on a flat piece of film can encode a three-dimensional image. This has profound implications for the information paradox we discussed earlier. If information is always encoded on the event horizon, then it's never truly lost inside the black hole. As the black hole evaporates and the horizon shrinks, the information is released with the Hawking radiation. The interior and exterior descriptions are related in such a way that information conservation is maintained, even though it might not be obvious from a purely classical description. The holographic principle is one of the deepest insights to come from black hole physics. It suggests that space itself might not be fundamental, that dimensionality might emerge from more basic principles. It connects quantum mechanics, gravity, information theory and thermodynamics in unexpected ways. And it's all thanks to thinking carefully about what happens inside black holes, about how information is stored, about how quantum mechanics and general relativity fit together. These objects, so extreme and remote, have taught us something profound about the nature of reality. We've talked about how time behaves strangely near black holes, how it slows down from the perspective of outside observers, how it becomes mixed with space inside the event horizon. But there's another aspect of time near black holes that's worth contemplating, something that touches on the very nature of what it means for time to pass, for change to occur, for the universe to have a history. This is the question of what time means at the singularity itself, and whether time ends there or continues in some transformed way. In general relativity, the the singularity is a place where geodesics terminate. If you follow the path of an infalling particle, tracing its trajectory through spacetime, that path ends at the singularity in a finite proper time. The particle's clock ticks a finite number of times, and then there are no more ticks. The world line, the particle's path through spacetime, simply stops. This suggests that time itself ends at the singularity, at least for anything that reaches it. But what does it mean for time to end? In our everyday experience, time is so fundamental that the idea of it ending seems almost meaningless. Time is the dimension in which change happens, in which cause precedes effect, in which we experience the flow of moments from past to future. If time ends, does change end? Does existence end? What could it mean for there to be a place where time simply isn't? Some physicists take the view that the singularity represents a true edge of space-time, a boundary beyond which there is no _quote, _6 time and space both end there, and asking what comes after is like asking what's north of the North Pole. The question doesn't make sense because quote 7 implies time, and time has ended. This view treats the singularity as a genuine feature of the universe, a place where existence itself terminates. Others suggest that the singularity is a signal that our theories have broken down. The infinite densities and curvatures predicted by general relativity are hints that we've pushed the theory beyond its domain of validity. Just as Newton's gravity fails near black holes and must be replaced by Einstein's general relativity, perhaps Einstein's theory fails at the singularity and must be replaced by quantum gravity. In the full theory, time might not end at all. It might continue, but in a way that our current mathematics can't describe. There's also the question of what time means inside the event horizon when the singularity is in your future. In normal space-time, the future is uncertain until it happens. You have choices about what to do, and those choices affect future outcomes. But inside a black hole, the singularity is your inevitable future. All paths lead there. Does this mean your future is completely determined? Do you have any freedom of action, any ability to choose? When your ultimate destination is fixed, philosophically this raises questions about determinism and free will, but in a more extreme context than we usually consider them. Outside a black hole, the laws of physics are deterministic in the sense that if you know the complete state of the universe at one time, you can calculate the state at any other time. But practically, we never know the complete state, and quantum mechanics introduces uncertainty. Inside a black hole, the destination is clear. The singularity is coming. You can't choose whether to reach it. You can only choose what you do during the finite time before you get there. This might sound grim, but there's another way to think about it. We're all moving toward futures we can't entirely control. We all face uncertainties and inevitabilities. The singularity is an extreme example, but it's not fundamentally different from the fact that all our lives have endings. What matters isn't the inevitability of the destination, but what we do along the way. Inside a black hole, that time before the singularity is limited and finite, but it's still real time, with real experiences and real choices within the constraints of physics. Time near black holes shows us that our intuitive understanding of time, built from everyday experience, might not capture all that time can be. Time can slow, time can mix with space, time can end or transform. These aren't failures of time, but extensions of it, ways that time behaves in conditions far removed from our ordinary lives. Understanding them requires us to let go of some of our assumptions and follow where the mathematics leads. And that mathematics leads us next to consider the strangest times and places in the universe. Black holes haven't always existed. There was a time in the early universe when no black holes had yet formed. The universe was filled with hydrogen and helium, the products of the Big Bang, but no stars had yet collapsed to create stellar mass black holes, and no supermassive black holes lurked at the centres of galaxies. Understanding when and how the first black holes formed is an active area of research, and it connects to some of the deepest questions about cosmic history. The very first stars, called Population 3 stars, formed from pristine gas that contained no heavy elements. These stars were likely much more massive than typical stars today, perhaps hundreds of times the Sun's mass. When such massive stars exhaust their nuclear fuel, they collapse directly to black holes without any intermediate stages. Some might have exploded as supernovae first, but others might have collapsed quietly, the core imploding past the neutron star stage to form black holes. These would have been the first black holes, formed perhaps just a few 100 million years after the Big Bang. As more generations of stars formed and died, more black holes would have accumulated. Some of these black holes would have merged when their host stars were in binary systems. Others would have wandered through space, occasionally capturing gas or encountering other objects. Over time, some of these stellar mass black holes found their way to the centres of forming galaxies, where they could grow by accreting matter from their surroundings. But this process seems too slow to explain the supermassive black holes we observe in the early universe. Quasars, those brilliantly luminous objects powered by black holes accreting matter, have been observed in galaxies formed less than 1 billion years after the Big Bang. The black holes powering these quasars contain billions of solar masses. Growing such massive black holes from stellar mass seeds in less than 1 billion years requires nearly continuous rapid accretion, and it's not clear that conditions would allow this. This has led astronomers to consider alternative formation scenarios. Perhaps some supermassive black holes form directly from the collapse of massive gas clouds, without the intermediate stage of star formation. In the early universe, under certain conditions, a large cloud of gas might collapse directly to form a black hole of thousands or even hundreds of thousands of solar masses. These intermediate mass black holes could then grow to supermassive proportions through continued accretion. Another possibility involves dark matter, the mysterious substance that makes up most of the universe's mass but doesn't interact with light. Some theories suggest that dark matter might collapse into dense structures in the early universe, and these structures might then collapse to form black holes. These dark matter black holes could serve as seeds for supermassive black holes, growing as normal matter fell into them. The truth is, we don't fully understand how supermassive black holes formed, especially the ones we see in the very early universe. It's one of the puzzles that drives current research in astrophysics. New telescopes, like the James Webb Space Telescope launched in 2021, are observing the early universe with unprecedented clarity, finding galaxies and quasars from times we've never been able to study before. These observations will help us understand how black holes formed in the cosmic dawn. What's fascinating is that these early black holes, formed in the universe's first billion years, still exist today. Black holes don't age in the usual sense. They can grow by accreting matter, they can merge with other black holes, but they don't deteriorate or die unless they evaporate through Hawking radiation, a process that takes longer than the current age of the universe for any black hole we've observed. So the supermassive black hole at the centre of our galaxy, Sagittarius A star, might have formed in the early universe, back when the cosmos was young and galaxies were just beginning to take shape. Inside these ancient black holes is matter from the early universe, matter that fell in billions of years ago when the universe was hot and dense and filled with young stars. That matter has been falling toward the singularity all this time, or perhaps has already reached it, compressed to densities we can't fathom. The black holes are time capsules in a sense, containing within them the history of cosmic evolution, though that history is hidden forever behind event horizons. This connection between black holes and cosmic history reminds us that these objects aren't static. They have life cycles, from formation to growth to eventual evaporation. They're part of the universe's story, woven into its evolution. Behind everything we've discussed, underlying all our understanding of black holes, is mathematics. Einstein's field equations, the Schwarzschild and Kerr solutions, the calculations of Hawking radiation, the formalism of quantum field theory in curved spacetime. All of this is expressed in the precise language of mathematics. For some, this mathematics is beautiful in its own right, elegant and deep. For others, it's a tool, a way to make predictions about the physical world. But for everyone who studies black holes seriously, the mathematics is essential. It's how we explore regions we can never visit, how we reason about phenomena beyond direct experience. Einstein's field equations relate the curvature of spacetime to the distribution of matter and energy. They're 10 coupled nonlinear partial differential equations, and solving them exactly is possible only in cases with high symmetry. The Schwarzschild solution, for a non-rotating black hole, was the first exact solution discovered. It has spherical symmetry, and this symmetry makes the equations solvable. The Kerr solution, for a rotating black hole, has axial symmetry and is more complex but still solvable. For more general cases, with irregular distributions of matter or time-varying fields, the equations can only be solved numerically, using powerful computers to approximate the solutions. What's remarkable is how much we can learn from these solutions without needing to solve every possible case. The Schwarzschild and Kerr solutions describe idealized black holes, perfectly symmetric and isolated. Real black holes aren't perfectly symmetric. They're surrounded by matter, they're moving through space, they're interacting with their environments. But the idealized solutions capture the essential features: the event horizon, the singularity, the geodesics of infalling matter. These exist in real black holes much as they do in the idealized solutions. The mathematics gives us a framework to understand the real objects. The mathematics also reveals features that we might not have anticipated. Time dilation. The slowing of time in gravitational fields emerges from the metric, the mathematical object that describes the geometry of spacetime. You don't have to postulate time dilation separately. It's a consequence of how spacetime curves. Similarly, the inevitability of the singularity for infalling matter follows from the mathematics of geodesics in curved spacetime. You don't have to assume the singularity. It emerges from solving the equations. This is part of the power and beauty of mathematical physics. The equations constrain what's possible. They make predictions, and those predictions can be tested, at least for aspects of black holes we can observe from outside. We can't observe the interior directly, but we can observe the effects of black holes on their surroundings, the orbits of stars around them, the radiation from their accretion disks, the gravitational waves from their mergers. Every observation that matches the predictions of general relativity gives us more confidence that the theory is correct, even for aspects we can't directly test. But the mathematics also has limits. At the singularity, the equations produce infinities, and infinities usually signal that a theory has reached the edge of its domain. The mathematics itself is telling us that it can't describe what happens at the very centre. This is frustrating, but also exciting. It means there's more to discover, new physics beyond general relativity that will complete the picture. Efforts to develop this new physics, to create a theory of quantum gravity, are themselves deeply mathematical. String theory, loop quantum gravity, and other approaches all rely on advanced mathematics, on concepts from topology, differential geometry, quantum field theory, and more. The theories are tested not through direct experiment, at least not yet, but through mathematical consistency. Do they reduce to general relativity in the appropriate limits? Do they preserve unitarity, the principle that probabilities add up to 1? Do they make any predictions that could be tested, even indirectly? This is physics at its most abstract, far removed from the laboratories and telescopes that most physicists use daily. It's physics driven by mathematics, by the desire for consistent and complete theories. Some find this troubling, worried that physics is becoming untethered from experiment. Others see it as necessary, as the only way to make progress on questions that can't be answered through direct observation. Black hole interiors are the ultimate test case for this approach. We'll never observe them directly. We can only understand them through theory, through mathematics, through the careful reasoning that has been the hallmark of physics since Newton. And that brings us to the question that has guided this entire journey. What, ultimately, have we learned about what's inside a black hole? What can we say with confidence, and where does uncertainty remain? After all this exploration, after journeying from the formation of black holes to the quantum mechanics near singularities, it's time to step back and consider what we actually know. Not what we speculate, not what theories suggest might be true, but what we can state with confidence based on solid observation and well-tested theory. This is the bedrock, the foundation on which all further speculation must build. We know that black holes exist. This isn't speculation anymore. We've observed stellar mass black holes in binary systems, where we can measure their masses and watch matter fall into them. We've observed supermassive black holes at the centres of galaxies, including our own. And in 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the dark region surrounded by a bright ring of photons captured in orbits around the event horizon. That image, from the supermassive black hole in the galaxy M87, confirmed predictions from general relativity in striking detail. We know that black holes have event horizons, boundaries beyond which light cannot escape. We've never directly observed an event horizon, because by definition it doesn't emit light. But we've observed matter disappearing beyond certain radii. We've seen the X-rays and other radiation produced as matter heats up while falling in, and all of these observations match the predictions of what should happen around an event horizon. The indirect evidence is overwhelming. We know that space-time near black holes is severely curved. We can observe this curvature through gravitational lensing, where light from background objects is bent around the black hole, creating distorted images or multiple images of the same object. We can observe it through the orbits of stars near supermassive black holes, orbits that move much faster than Newtonian gravity would predict, orbits that precess in ways that match Einstein's equations perfectly. We know that black holes merge and emit gravitational waves. Since 2015, the LIGO and Virgo detectors have observed dozens of black hole mergers, events where two black holes spiral together and combine into a single larger black hole. These observations have confirmed that gravitational waves exist, that they propagate at the speed of light, and that their properties match the predictions of general relativity to extraordinary precision. We know that matter falling into a black hole is compressed and heated. We observe accretion disks around black holes, glowing disks of matter spiralling inward. We observe jets, streams of particles ejected at near-light speed from the regions around supermassive black holes. We observe X-rays and gamma rays, produced when matter is heated to temperatures of millions or billions of degrees. All of this tells us that matter doesn't just fall calmly into black holes. It interacts violently with itself and with the extreme gravitational field on its way in. We know that time slows near black holes. This time dilation has been measured directly in strong gravitational fields, though not yet near actual black holes, but we observe it indirectly through the way that processes near black holes appear slowed from our perspective, through the redshift of light coming from deep in gravitational wells. The mathematics that predicts this time dilation is the same mathematics that accurately describes every other gravitational phenomenon we've tested. These are the things we know with high confidence. They're based on observation, on measurements, on the consistent success of general relativity in describing gravitational phenomena across a huge range of scales and conditions. General relativity has been tested in solar system experiments, in binary pulsar systems, in gravitational wave observations, and it has passed every test. Its predictions about black holes, at least about the observable aspects of black holes, have been confirmed repeatedly. But notice what's missing from this list. We don't have direct observational evidence about what happens inside event horizons. We can't observe the singularity. We can't directly measure Hawking radiation, though we have strong theoretical reasons to believe it exists. We can't test the predictions of quantum gravity, because we don't yet have a complete theory of quantum gravity. Everything about the interior of a black hole, about what happens as you approach the singularity, remains theoretical, based on extrapolating theories that work well in the conditions we can test. This doesn't mean the theories are wrong. It means we're reaching the limits of what observation can tell us, and we're relying more heavily on the mathematics and the logic of the theories we trust. And that brings us to consider what we don't yet know, where uncertainty remains. For all that we've learned about black holes, there's still so much we don't understand. The interior of a black hole remains one of the great unknowns in physics, a place where our best theories give us hints and suggestions, but not definitive answers. Let's consider the major open questions, the places where uncertainty remains and where future discoveries might surprise us. We don't know what happens at the singularity. General relativity predicts infinite density and infinite curvature, but infinities in physics usually indicate that a theory has reached its limits. Most physicists believe that quantum effects become important at or near the singularity, smoothing out the infinities into something extreme but finite. But without a complete theory of quantum gravity, we can't make precise predictions. We don't know if there's a smaller scale of space and time. We don't know if the singularity is really a point or a small region. We don't know what form matter takes under such extreme conditions. We don't know how information is preserved when matter falls into a black hole. The information paradox remains unresolved, despite decades of work by some of the best physicists in the world. We have promising ideas. The holographic principle suggests information is encoded on the event horizon. Quantum entanglement might play a role, but we don't have a complete, universally accepted solution. The debate touches on fundamental issues about how quantum mechanics and gravity fit together. We don't know whether event horizons have firewalls. The Firewall Paradox reveals tensions between different principles in physics, and we don't yet know which principle to trust when they seem to conflict. Does the equivalence principle hold, allowing smooth crossing of the horizon, or does quantum mechanics require a violent high-energy boundary? Different physicists give different answers, and there's no observational way to test them directly. We don't know whether the interior of a black hole contains wormholes or other exotic structures. The mathematics allows such structures, but the mathematics also allows many things that might not actually occur in nature. We need more observations, more complete theories, before we can say whether wormholes exist, whether they're related to black holes, whether they're traversable or merely mathematical curiosities. We don't fully understand how supermassive black holes formed. We've observed supermassive black holes in the early universe, less than 1 billion years after the Big Bang, containing billions of solar masses. Growing such massive black holes in such a short time is challenging, and while we have theories, direct collapse or intermediate mass seeds, we don't have definitive answers. Future observations, particularly from advanced telescopes studying the early universe, will help clarify this. We don't know if there are primordial black holes that might have formed in the early universe from density fluctuations rather than stellar collapse. If they exist, they could range from very small, perhaps asteroid mass or smaller, to large, perhaps thousands of solar masses. Some physicists have speculated that primordial black holes might make up some or all of dark matter, but we've never detected one. The question remains open. We don't know what happens when a black hole completely evaporates. If Hawking radiation is real, and most physicists believe it is, then every black hole will eventually radiate away all its mass. But what happens at the very end? Does the black hole disappear completely, leaving nothing but radiation? Does a tiny remnant remain, a Planck-scale object containing information about everything that fell in? Different approaches to quantum gravity give different answers, and we don't have a way to test them. We don't know how to merge general relativity and quantum mechanics into a single consistent theory of quantum gravity. This is perhaps the deepest open question, and black holes are the primary testing ground for any attempt at an answer. String theory, loop quantum gravity, and other approaches all offer possible frameworks, but none is complete. None has made testable predictions that clearly distinguish it from the others. The problem is hard, involving mathematics and concepts that push the boundaries of what we understand. These unknowns aren't failures, they're frontiers. They're the places where physics is growing, where new discoveries wait. Every unknown question is an opportunity for future understanding. Every mystery is an invitation to think more deeply, to develop better theories, to find new ways of probing the universe. And in a sense, these unknowns are part of what makes black holes so compelling. They're not solved problems, catalogued and filed away. They're active mysteries, drawing the attention and imagination of physicists around the world. There's a temptation, when faced with unknowns, to feel frustrated, to wish we had more answers, to see uncertainty as a kind of failure. But I want to suggest a different perspective. There's beauty in uncertainty, value in living with questions we can't yet answer. The mysteries of black hole interiors aren't gaps in our knowledge to be embarrassed about. They're opportunities for wonder, spaces where imagination and reason can explore together, where we're reminded that the universe is richer and stranger than any single generation's understanding can capture. Think about what it means to genuinely not know something. In most of our daily lives, we have access to answers. If we want to know what time the sun rises tomorrow, we can look it up. If we want to know how far away the moon is, we can find the number. If we want to know how proteins fold or how economies grow, there are experts who have studied these things and can explain them to us. We live in an age of extraordinary knowledge, where the accumulated understanding of humanity is available at our fingertips. But black hole interiors are different. No amount of searching will give you a definitive answer to what happens at a singularity, because we don't have one yet. No expert can tell you with certainty whether firewalls exist, because it's still being debated. No book contains the complete theory of quantum gravity, because it hasn't been developed yet. These are genuine unknowns, places where human knowledge hasn't yet reached, where the next generation of physicists will be the ones to make progress. And there's something thrilling about that. It means discovery is still possible, that understanding isn't complete, that the universe still has secrets to reveal. For anyone drawn to physics, to science more broadly, this should be exciting rather than frustrating. It means there's work to be done, puzzles to be solved, insights to be gained. The unknowns about black holes are opportunities for future careers, for future breakthroughs that will reshape how we think about space-time and quantum mechanics and the nature of reality itself. But even for those of us who won't personally solve these problems, who won't spend our careers working through the mathematics of quantum gravity, there's value in contemplating the mysteries. They remind us that our understanding of the universe is provisional, always subject to revision as new evidence comes in and new theories are developed. They teach intellectual humility, the recognition that we don't know everything, that our current theories might be incomplete or wrong in important ways. This humility is important because it keeps us open to surprise, to the possibility that reality might work differently than we expect. History is full of examples where physics took unexpected turns. Einstein's relativity overthrew the Newtonian worldview that had seemed so solid. Quantum mechanics reveal that reality at small scales is probabilistic and uncertain, not deterministic and predictable. These weren't just minor adjustments. They were revolutionary changes that forced physicists to rethink their most basic assumptions. And they happened because physicists were willing to follow the evidence and the mathematics wherever they led, even when that meant abandoning cherished ideas. Black hole interiors might be another place where such revolutions happen. The next breakthrough in quantum gravity, whenever it comes, might force us to rethink what we mean by space and time, by matter and energy, by information and entropy. It might reveal that space-time is emergent from something more fundamental, that dimensions we experience are projections from lower dimensional descriptions, that the smooth continuum of space is actually discrete and grainy at small scales. We don't know what the breakthroughs will show. That's part of why they're breakthroughs. In the meantime, we can appreciate the mystery for what it is, a reminder of the universe's depth and complexity, of the limits of current knowledge, of the ongoing nature of scientific inquiry. We can enjoy the speculation, the thought experiments, the competing theories that physicists debate. We can marvel at how far we've come, from Newtonian gravity to Einstein's curved spacetime to Hawking radiation, while acknowledging how far we still have to go. There's a peace to be found in this acceptance of uncertainty. Not everything needs to be known right now. Not every question needs an immediate answer. Some mysteries can be lived with, contemplated, appreciated. The singularity at the heart of a black hole can remain mysterious, at least for now, and that's okay. The universe isn't obligated to make itself fully comprehensible to us, and perhaps part of its beauty lies in its resistance to complete understanding. So let's appreciate what we know, remain curious about what we don't, and find satisfaction in both. We've journeyed deep into the nature of black holes, into the heart of space-time's most extreme phenomena, and now it's time to come back to ourselves, to consider what all of this means for us, for humans living on Earth in the early 21st century, looking up at stars that contain black holes we'll never visit. What does it mean to understand, even partially, what happens inside a black hole? What does it tell us about our place in the universe? One thing it reveals is the remarkable capacity of human reason. We can't travel to black holes. We can't survive their environments. We can't probe their interiors directly. And yet we can describe them, predict their properties, understand the physics that governs them. This is possible because of mathematics, because of the scientific method, because of the accumulated work of generations of physicists building on each other's insights. We've reached across billions of light years and billions of years of time to describe objects so extreme they warp reality itself. That's extraordinary. This capacity for understanding is perhaps humanity's most distinctive feature. We're not the strongest species. We're not the fastest. We don't have the keenest senses or the longest lifespans, but we can understand. We can look at the universe around us, notice patterns, formulate theories, test those theories, and gradually build up accurate descriptions of how reality works. Black holes are one of the ultimate tests of this capacity. They exist in conditions far removed from everyday experience, described by physics at the extremes of what's possible. Yet we can grasp them, at least conceptually. We can write down the equations and understand what they imply. This understanding also reveals our smallness. Black holes operate on scales that dwarf human concerns. The event horizon of Sagittarius A star, the black hole at our galaxy's centre, is millions of kilometres across. The tidal forces near stellar mass black holes are so powerful they would shred a human body in an instant. The timescales of black hole evaporation are so long, they make the age of the universe seem like a fleeting moment. We're incredibly tiny and brief compared to these cosmic phenomena. But smallness isn't the same as insignificance. Yes, we're small and brief, but we're the ones asking the questions. We're the ones trying to understand. As far as we know, we're the only part of the universe that has developed the capacity to comprehend black holes, to write equations describing singularities, to debate the Firewall Paradox. This makes us, in a sense, the universe becoming aware of itself, consciousness emerging from unconscious matter and energy, and looking back at the cosmos with curiosity and wonder. There's a kind of defiance in this. The universe doesn't care whether we understand it. Black holes don't exist for our benefit. The laws of physics don't make themselves easy to discover, and yet we persist in trying to understand anyway. We build telescopes, we train physicists, we dedicate careers and lifetimes to figuring out how reality works. This pursuit of knowledge for its own sake, this insistence on understanding even things that have no practical application, might be the most distinctively human activity there is. And in understanding black holes, in grappling with singularities and event horizons and quantum mechanics in curved space-time, we're changed. We can't encounter ideas this profound without being affected by them. Our sense of what's possible expands. Our intuitions about time and space are challenged and refined. We're forced to think about existence in new ways, to consider realities far outside our everyday experience. This is part of what makes science valuable, not just for the practical applications it enables, but for how it changes our understanding of ourselves and our place in existence. We live on a planet orbiting an ordinary star in an unremarkable galaxy, containing billions of stars and probably millions of black holes. The nearest black hole to us is probably thousands of light years away. We'll never visit one. We'll never see directly what happens inside one. But we can understand them, and that understanding is its own reward. It connects us to the cosmos, makes us part of the universe's story, gives our brief lives a kind of meaning that transcends their physical scale. So when we look up at the night sky, knowing that out there, hidden among the stars, are black holes with their warped space-time and mysterious interiors, we can feel simultaneously humbled and elevated. Humbled by the scale and strangeness of it all, elevated by our capacity to comprehend it. Both feelings are appropriate, and both are part of what it means to be human in a universe containing black holes. Every journey must end, even a journey toward infinity, even a journey toward a singularity where time itself might stop. We've travelled together from the formation of black holes, through the crossing of event horizons, toward the mysteries of singularities and the frontiers of quantum gravity. We've contemplated what we know and what we don't, what physics tells us, and where physics admits its limitations. Now, as we approach the end of our time together, let's reflect on what this journey has meant, what we've learned, what remains mysterious, and why that's not just acceptable, but beautiful. Black holes are endings, in a sense. They're where stars end their lives, where matter ends its journey as recognizable particles, where space-time curves so severely it creates boundaries beyond which return is impossible. Inside a black hole, all futures lead to the singularity. Time itself, in the form we understand it, might end there. These are genuine endings, not metaphorical ones. Something that falls into a black hole doesn't come back out. Information might be preserved somehow, encoded on horizons or in Hawking radiation, but the object itself is gone, transformed beyond recovery. But black holes are also beginnings. They're laboratories where physics reaches its limits and must evolve to describe new regimes. They're the test cases that drive the development of quantum gravity, that force us to think about space-time in new ways, that reveal connections between gravity and thermodynamics, between geometry and information, between the very large and the very small. Every puzzle about black holes is an opportunity for new physics, for insights that might reshape our understanding of reality. The question we started with, quote 8, doesn't have a complete answer yet. We can describe the journey toward the singularity using general relativity. We can calculate geodesics, predict tidal forces, understand time dilation. But at the singularity itself, our theories break down. We can't say with certainty what happens there, because we don't have the full theory of quantum gravity that would describe it. This incompleteness is frustrating if you demand definitive answers to every question. But it's also exhilarating if you appreciate the ongoing nature of discovery. What we can say is that inside a black hole, space-time behaves in ways that challenge our intuitions. Time and space trade roles. The singularity is your future, not your destination in space. Tidal forces stretch matter to extraordinary degrees. Quantum effects, invisible in everyday life, become crucial. The physics is extreme, but it's still physics, still governed by laws we can write down and reason about. Black holes aren't violations of natural law. They're natural law pushed to its absolute limits. And perhaps that's the deepest lesson. The universe has laws, patterns, regularities that we can discover and describe. These laws apply everywhere, from the smallest quantum fluctuations to the largest cosmological scales, from the coldest reaches of intergalactic space to the hottest interiors of black hole accretion disks. By understanding these laws, by following them into extreme conditions, we learn what reality is made of at the deepest level. Black holes are extreme enough that they force us to confront the foundations of physics, to ask what space and time really are, what matter and energy really are. what information and entropy really are. So the answer to _quote_9_ is multi-layered. There's the answer from general relativity. Space-time curves severely, geodesics terminate at a singularity, tidal forces grow without bound. There's the answer from quantum mechanics. Information must be preserved somehow. The singularity might be smoothed by quantum effects. The event horizon might be more complex than it appears. And there's the answer from honesty. We don't fully know yet. We're still working it out. The final theory that resolves all the paradoxes and answers all the questions hasn't been written. All three of these answers are true in their own way, and living with all three simultaneously, holding the knowledge and the uncertainty together, is part of what it means to engage with science seriously. We know enough to be amazed, to appreciate the universe's strangeness and beauty. We don't know enough to stop being curious, to stop asking questions, to stop pushing at the boundaries of understanding. This is where we are, here at the end of our journey, full of wonder at what we've learned and full of curiosity about what remains to be discovered. And that brings us to the end, to the good night, to the moment when I release you from this long contemplation of black holes and singularities and the edges of space-time, sending you gently towards sleep with the cosmos still turning in your thoughts. Thank you for staying with me through this entire journey. We've spent more than 2 hours together, drifting through the cosmos, contemplating the most extreme objects in the universe, asking what happens in places no human will ever visit. That you've stayed this long, that you've accompanied me through event horizons and singularities, through firewalls and holographic principles, through mathematical abstractions and physical extremes, means something. Thank you for your curiosity, your patience, your willingness to contemplate mysteries that don't have easy answers. We've travelled from the collapse of stars to the evaporation of black holes, from the event horizon to the singularity itself, from what we know with confidence to what we can only speculate about. We've seen how gravity warps space-time, how time dilates and dimensions trade places, how quantum mechanics and general relativity clash in profound ways. We've contemplated information paradoxes and Hawking radiation, wormholes and holographic principles, the formation of the first black holes and the distant future when they might be the last objects remaining. The answer to the question we started with, quote, 10, is both simpler and more complex than you might have expected. Simply, matter falls toward the singularity, space-time curves increasingly severely, and eventually our theories break down. In complexity, quantum effects might smooth the singularity, information might be preserved in ways we don't yet understand, the interior might connect to other regions of space-time, time and space might behave in ways that transcend our current descriptions. The universe, it seems, is not obligated to make itself easy to understand, and black holes embody this beautifully. Perhaps the deeper answer is that black holes teach us about the limits of knowledge and the persistence of wonder. They show us that the universe is larger and stranger than our theories can fully capture, that there are genuine mysteries remaining, that discovery is ongoing. They remind us of our smallness in the cosmic scale, while simultaneously demonstrating the remarkable power of human reason to understand even what we cannot observe directly. What happens inside a black hole is, in some sense, beyond our current knowledge. And that's not a failure. It's an invitation to future understanding, a space for continued curiosity, a reminder that science is a process, not a finished product. If you've enjoyed this slow drift through cosmic mysteries, A-Like helps others find these contemplative explorations. And if you have thoughts or questions, if something we discussed resonated with you or puzzled you, the comments are always open. To those already subscribed, thank you for being part of this community of curious minds seeking both knowledge and rest. Wherever you are in the world right now, whatever room you're in, whatever surface you're lying on, I hope you found some measure of peace in these past hours. I hope your breathing has slowed to match the vastness we've been contemplating. I hope your thoughts have quieted, replaced by the gentle drift towards sleep that was always our ultimate destination. Look up at the night sky, if you can from where you are, or picture it in your mind if you can't. All those stars, some of them nearing the end of their lives, some already having collapsed into black holes we can't see, all that space between them, curved and warped by gravity, following laws we've spent centuries uncovering. All that time, billions of years past and billions more to come, with black holes as patient witnesses to cosmic evolution. And here you are, a collection of atoms that briefly became conscious, briefly became capable of understanding, briefly paused to contemplate what happens at the edge of everything before returning to the rest we all need. There's a kind of peace in that, in being part of something so vast and so indifferent and yet so comprehensible through the power of reason and observation. We understand black holes not despite their extremity, but because of it. They force physics to reveal itself most clearly. And in understanding them, even partially, we understand something about the nature of reality itself. Sleep well. Dream of curved space-time if you dream at all. Dream of event horizons and singularities, of geodesics ending and beginning, of time flowing strangely in gravitational wells. Dream of mysteries solved and mysteries remaining, of what we know and what we've yet to discover. Dream of the universe continuing its patient expansion, while black holes slowly evaporate, carrying within them secrets we're only beginning to glimpse. Good night. Thank you for travelling with me to the edge of everything. May your rest be deep, your dreams peaceful, and your wonder at the cosmos undiminished when you wake.